Hey folks, let's talk about water vapor pressure. Now, why on earth would we want to do that? Well, we're certainly curious about water vapor pressure. It has a tremendous impact on climate. We usually don't think about that, but the vapor pressure of water does affect things like cloud cover and rainfall patterns and such. And we're particularly interested with global warming and what will happen to the water vapor pressure with warming. We know it will increase, but by how much? And how will that affect our climate? So in this video, what we're going to do is we're going to learn how to calculate the increase in water vapor pressure that occurs when we increase the temperature. We're going to use a conservative estimate of a 2-degree temperature rise by the end of the century due to global warming. We know that that's an estimate and it is conservative. It could be more than that if we don't do something to halt or at least slow the pumping of greenhouse gases into the atmosphere. So we'll calculate how much the water vapor pressure increases when we increase the temperature. Now, exactly how will we do that? Well, we have to first recognize that when we talk about vapor pressure, what is it we're talking about? We're talking about an equilibrium between the liquid and the vapor. All right, so we have H2O liquid in equilibrium with H2O vapor. And we know the Gibbs energy tells us that when these two are in equilibrium, their Gibbs energies are the same. So we have the Gibbs energy of the liquid is equal to the Gibbs energy of the vapor. Now, one thing to look at here as we discuss this is the fact that we are talking about 1 bar pressure for our liquid, standard conditions. For the vapor, it's not standard because the vapor pressure is in fact lower than 1 bar. And we're going to first figure out exactly what the Gibbs energy is at pressures lower than 1 bar. So how do we do that? Well, we know that the Gibbs energy depends on temperature and pressure according to this expression. The temperature dependence depends on the entropy. The pressure dependence depends on the volume. All right. Well, we're going to first look at what happens with the pressure dependence. Obviously, we're going to be looking at the temperature dependence because that's the whole point to what we're doing here, is to figure out exactly what happens when we change the temperature. But we first need to figure out what the Gibbs energy is of the vapor at our starting point, at our initial temperature before we increase it. All right. So now we can see that this is the relationship, assuming an ideal gas. We can show that the Gibbs energy at a pressure different from 1 bar of the vapor is given by this expression where the vapor pressure at our initial temperature is given by P sub I. All right. And I won't go through the derivation of this, that we did this in a previous video. So this is assuming an ideal gas. This would be our relationship that would give us the Gibbs energy of the vapor at our initial temperature at the initial vapor pressure. So we know that then, therefore, because the liquid vapor pressure, because the liquid Gibbs energy is equal to the vapor Gibbs energy at equilibrium, therefore the liquid Gibbs energy is equal to that expression, which incorporates the initial vapor pressure of our water. Okay, so that's where we are. This is the starting point at the initial temperature. All right, so what about the temperature dependence? We'll take a look at the liquid first. In the case of the temperature dependence, we are looking at the first term here, and that depends on the entropy. All right, so again, based on that, assuming that the entropy does not change significantly with the temperature change, and that's a reasonable assumption since we're talking about a 2-degree change. If it was larger, clearly we'd have to be looking at how the entropy changes. But we are assuming that the entropy change is small for the liquid over this change in temperature. So assuming that, when we integrate our expression above, this is what we get. So if we increase the temperature by 2 degrees, the Gibbs energy of the liquid at a 2-degree higher temperature is related to the initial temperature through this expression. And again, it depends on the entropy of the liquid. All right, so now we have is a situation where here is the expression that we looked at in the previous slide, where we've got the Gibbs energy of the liquid at the final temperature, all right, related to the temperature change and its entropy, all right. And we also know that the Gibbs energy of the liquid at the initial temperature is related to the Gibbs energy of the vapor at the initial temperature, all right. So we can take that expression and substitute it into the top expression. And we get this overall expression here, which shows the Gibbs energy of the liquid at the elevated temperature, all right, related to the Gibbs energy of our vapor at the initial temperature, and the vapor pressure at the initial temperature, all right? So again, this is going to be the Gibbs energy of the liquid at the elevated temperature related to the vapor and the entropy of the liquid, all right? So we're kind of plowing through some equations here. I'm hoping that you're following this. Certainly, please ask questions if you're not. Our goal here is going to be to derive an overall equation for the change in vapor pressure, and we'll leave the calculation actually for you to do at a later point. So let's take a look at the vapor at elevated temperature. So this is what we know, that we can relate the Gibbs energy of the vapor at our elevated temperature T sub F to the standard Gibbs energy at 1 bar pressure and the vapor pressure at that elevated temperature. And that's the critical component here. That is the pressure we're trying to calculate. What is that vapor pressure at the elevated temperature? So that's what we know. All right. So how does then the Gibbs energy of the elevated temperature compare to the Gibbs energy at the initial temperature? Well, we know the temperature dependence, as we've already discussed, is dependent on the entropy of the vapor here, as we see. So this is just the standard relationship that we looked at when we were talking about the liquid. We compare with the Gibbs energy, the standard Gibbs energy at the elevated temperature is equal to the standard Gibbs energy at the initial temperature minus this correction term based on the entropy that we see right here. So that's going to be the critical factor here that we're looking at. All right, so now if we just go ahead and take our equation for the standard Gibbs energy at the elevated temperature and plug it into the first equation here on this slide, this is what we get. So now we have the Gibbs energy of the vapor at the elevated temperature compared to the standard Gibbs energy at the initial temperature. We have the temperature correction due to the entropy. And again, what we're assuming here is that for a relatively small temperature change, the entropy does not change significantly, so we are assuming that it's constant. Of course, entropy does increase as the temperature increases, but in this particular circumstance, it's a minor change. And since this is kind of a what we might call back of the envelope calculation anyway, the error introduced by that is pretty insignificant. All right, and then we have the pressure correction term here. And again, remember, this is what we're trying to calculate, this final pressure. All right, so let's start to take a look at the equilibrium that's occurring at the elevated temperature and start putting all these equations together. So we know that at equilibrium, again, the Gibbs energies are the same. In this case, here's the Gibbs energy of the liquid. We are again still assuming that it's standard pressure of 1 bar for the liquid, but as we know that that's not the case for the water because its pressure is not 1 bar. So that's going to be equal to the Gibbs energy of the vapor, the water vapor at the elevated temperature. And so that's what we're going to do is we're going to just go ahead and go back to the equations that we've already derived. Here is the Gibbs energy at the elevated temperature with our pressure term for the vapor and our correction due to the entropy for the liquid. All right, here's the equation we had on the previous slide for the vapor. So we've got our equation for the liquid, we've got our equation for the vapor, all right? And again, these two are equal according to the equilibrium. So we're going to put those two together. All right, again, making these two equal to each other. And this is what we get. On the left-hand side, we have the Gibbs energy of the liquid at the elevated temperature. On the right-hand side, we have the Gibbs energy of the vapor at the elevated temperature. And that's what we have. Now you'll notice that we can simplify this a little bit because the first term on each side is the same, so they'll cancel out. All right, are we having fun? We love these equations, don't we? All right, so now finally we're going to start putting it together. After canceling out those two terms on that previous slide, we're going to note that this is what we have for the liquid, this is what we have for the vapor after we've canceled the first two terms out. All right, so now we can just start doing some algebraic rearrangement. Remember, this is what we're trying to calculate, the final pressure. All right, so what we can do is we just are going to take the entropy terms, all right, we're moving the vapor, entropy vapor term algebraically over here to the left side of the equation, and combining those two, we end up with this, all right, and then we know that this is actually delta S of vaporization, right? It is the entropy of the vapor minus the entropy of the liquid, and that's just the delta S for the vaporization process. All right, and so that's what we have. Again, what we're trying to do is solve for this, so we're basically just algebraically now, we're dividing both sides of the equation by RTF. This is what we have, and now we're just going to solve for PF. And we know we can get rid of the natural log by raising everything to the natural number, or raising the natural number e to this both sides of the equation, and then just solving for p sub f. Okay, so now we can just do some simple algebraic rearrangement, getting rid of the natural log by, of course, using the natural number e here as indicated. And so just solving them for p sub f, this is what we get. P naught, of course, is 1 bar. Pressure, this is the entropy of vaporization, which is just the entropy of the liquid minus the entropy, the entropy of the vapor minus the entropy of the liquid. Here's the temperature differential, which again, we're going to start with a 2 degrees Celsius or 2 Kelvin difference in temperature there. This will be our initial temperature that we're starting at with our initial vapor pressure. And this, of course, is our final temperature. So I'm going to leave this calculation to you at a later point. You can do this by, you're going to have to do some things, you're going to have to look up some factors. We can assume, let's go ahead and assume that our initial temperature is 298 Kelvin. And our final temperature is 300 Kelvin. Not sure why the pen is making these weird things here. And so this is what we have. You will have to look up the entropy of vaporization, or you can simply look up the entropies of the liquid and the vapor to do that calculation. You will also have to look up the vapor pressure. This is going to be the vapor pressure of water at 298. So you can certainly look that value up to do the calculation and calculate the final pressure and how much of a difference is it, and is it going to be significant. So we're going to leave that to you, and we'll talk about this later.